Welcome back to the Explainer. So today, we're going to tackle a really crucial tool for engineers and scientists, the inverse Laplace transform. We're going to break down exactly how you travel from the abstract world of frequency all the way back to the real world of time.
Okay, so let's just dive right in. We've already seen how the Laplace transform can take these super tricky problems and simplify them by shifting us out of the time domain, f of t, and into the frequency domain, f of s. But that's only half the journey. To get an answer that actually means something in the real world, like, say, predicting how a circuit's voltage is going to change over time, we have to travel back. So the big question is, how?
And our tool for this return trip, well, it's the inverse Laplace transform. And yeah, as you might guess from the name, its whole job is to undo the original transform and bring us right back home.
It's this really elegant, simple relationship. If the Laplace transform of some function f of t gives you f of s, then taking the inverse Laplace transform of f of s gets you right back to where you started with your original f of t. It's a perfect round trip. As simple as that.
Now, the fantastic news here is that you don't need to be solving complex integrals every single time you do this. We have a map. Think of it like a mathematical decoder ring. It's called the table of transforms, so let's build out our toolkit from it.
Okay, so here's landmark number 1 on our map. This is the most fundamental path back you can take. The inverse transform of 1 over s is just the constant, 1. This is our home base, our starting point for everything else.
And these are the real workhorses of our toolkit. We've got our transform pairs for powers of t, for all those exponential functions, and of course, for our essential sine and cosine waves. Getting familiar with these is kind of like learning the basic vocabulary for this whole new mathematical language.
And our map even shows us how to handle more complex, kind of shifted functions. Anytime you see this s minus a pattern hanging out in the denominator, think of that as a signal flare. It's telling you that an exponential term, e to the at, is a part of the original function. Spotting this pattern is a huge, huge shortcut.
So this right here, this is absolutely crucial. This is the linearity property. I like to call it our superpower. It basically means we can take a complicated function that has a bunch of things added or subtracted, and we can just break it up into smaller, bite-sized pieces. We solve each one of those little pieces on its own, and then we just add the results back together at the end. This is the key that unlocks pretty much everything else.
Okay, let's put this into practice. We're going to start with level 1. This is where the function f of s that we're given looks a lot like an entry on our map, maybe with just a little twist.
All right, here's our first challenge. Find the inverse transform of 1 over s to the 4th. Now, if we look at our table, it doesn't quite match perfectly, at least not yet.
So we scan our map and we spot the powers of t rule. Our denominator is s to the 4th, right? And the rules form is s to the n plus 1. So if we just match those up, it's pretty clear that n plus 1 has to equal 4, which means our n must be 3.
Okay, but the table entry needs an n factorial up top. Since our n is 3, we need a 3 factorial. So here's the trick. We multiply by 3 factorial over 3 factorial, which is really just a clever way of multiplying by 1, right? This lets us perfectly match the form on our map. Then we can pull that constant denominator out, and we're left with the inverse of t cubed. Our final answer? T cubed over 6. See? Not so bad.
Ready for level 2? This is where we finally get to use that linearity superpower we were just talking about. We're going to break a problem apart.
Now this one looks a bit more complicated, doesn't it? And that's mainly because we've got an addition happening up there in the numerator. It doesn't really look like any single entry on our map.
But we know the secret. The key here is to use linearity to split this one big fraction into 2 separate, much easier problems that we do know how to solve.
So we just use our linearity superpower and split it into 2 fractions. The first piece, the one with the s on top, is a perfect match for our cosine rule. The second piece, with just a constant on top, well, it just needs a tiny adjustment to match our sine rule. We solve each one, add them together, and that's it. We're done.
All right, it is time for the boss level. What happens when the denominator is this complex product of a bunch of different terms? This is where a lot of people get stuck. But don't worry, we have a plan.
Take a look at this thing. The denominator has 3 distinct factors, all multiplied together. Yeah, that does not look like any form on our table. It looks intimidating, I get it, but we have a really powerful algebraic technique that lets us completely restructure this whole problem.
Okay, so here's the game plan.
It's a strategy called partial fraction decomposition. And the entire goal here is to take this one giant, complicated fraction and break it down into a sum of several small, simple fractions. And each of those simple fractions is one that we do know how to solve using our table.
The first step is a bit of algebra. We set up our decomposed form, and then, by plugging in some clever values for s, like s equals 1, s equals 2, and s equals -4, which makes different terms go to 0, we can quickly solve for those unknown constants a, b, and c. It's just a methodical process that cracks the code.
And here it is, the payoff. Our one really difficult problem has just been transformed into the sum of 3 very easy ones. Each little piece now has that simple form of a constant over s minus a. And we know from our map that each one of those transforms back into a simple exponential function.
So the crucial takeaway here is this. No matter how complicated a problem looks at first, the strategy is always the same. You simplify it, you break it apart, and you rearrange it until every single piece matches a known form on your transformation map. And there you have it. You've mastered the return journey. From simple matching all the way to partial fractions, you now have the tools to get back to reality. So the only question left is, where are you going to apply it first? Electrical circuits, mechanical vibrations, control systems, the possibilities are absolutely endless.